clinical applications.
Thank you. So it's a great pleasure to be here. In particular, I'd like to thank Dr. Wong, who's my program officer, for inviting me. I'm a clinician, so I should start out by saying, there's domain expertise. The cost of having somebody like me talk is that I have less domain expertise in a lot of this than most people in the audience. But the benefit is that I can provide context and just try to describe what the end application for some of these uses would be for healthcare. So these are my disclosures. Like I said, I'd like to thank the NIH for supporting our work. So functional neurosurgeons are doctors who invasively interact with neural circuitry. We usually think of the brain, but there's also the spine and peripheral nerve to measure and modify its computational purpose. Okay, we use this primarily with electrodes, tissue destruction, and then now with some emerging genomic tools. So to begin with, we had open surgeries, and we then used to do things like induced focal strokes. But over time, we've started to deliver high-frequency powered ultrasound or laser light to destroy structures that are involved with this circuitry, and then more recently to stimulate. Okay, so the level of intervention that we have is fairly crude compared with the levels of tools that we have for things like communication on our phones, for computing, and for communicating with one another. Okay, so medicine does lag, and a big purpose behind the lag is the need for safety and the need for validation prior to implementing things. When we intervene with the nervous system, it's always important to realize that there's a difference between treating the symptoms of a disease and changing the circuit dysfunctions that underlie the disease. From a practical perspective, that means that when we put devices in the brain, most often what we're doing now is delivering electrical current at very high frequency to disrupt an area, okay? But moving forward, we'd like to treat more nuanced diseases than we do now. So as we move from treating things like tremor, where we counteract a balance system that's perturbed on one end by damaging the other end, we want to start to treat psychiatric diseases. We're going to need approaches that that match the statistics of the brain, okay? And I think of this as what it means to be neuromorphic in the larger sense, and adapt to the dynamical state of the brain so that we can modify the way that the brain computes in real time, okay? And so for the second thing, which we're not doing yet, I think the type of approach people have talked about for neuromorphic systems and for embodiment may apply, and I'd like to show you some examples of that. So if I say, well, what's the use of a clinician when we have here? I can provide some context. I can describe a need that we have. But it's important to remember that the mission statement of the NIH and the mission statement of a lot of the institutions that deliver care is to meet a clinical need. But the mission statement for companies that make products, regardless of what they tell you, is they're bound by their charter to make a profit. And so we have to keep in mind that the way that we design things has to integrate into the economic picture, which more and more is playing a role in the types of ways that we can make decisions in a clinical context. And the economic incentives will drive what tools. It's not necessarily the best tool that we'll have to offer patients so much as the one that we have access to, and the economics drive the access that we often have. And that's also not the same thing as what might be scientifically compelling, right? So I'm a scientist in addition to being a surgeon. The things that interest me intellectually are often very different from the things that influence the decisions that I make about how to treat a particular child. And lastly, what's interesting to the public. Okay, so a lot of us here think about the messaging that we have for the public. That's different than the economics incentives. It's different than what patients need. And sometimes that's different than what interests us as people that are experts in our particular field. And so if we say, what does artificial intelligence have to offer us, offer a clinician, in particular a functional neurosurgeon? I think that we can use artificial intelligence for discovering structure, okay? And this is the kind of thing that I do in my group, which is electrophysiological signal decoding, but also trying to understand how different genetic predispositions determine the end phenotype that people will have in terms of their diseases, doing things like structural segmentation. documentation and chart synthesis, right? So we often think of this as the most boring thing that we would do, right? This is the most straightforward implementation that we could have for LLMs now. But this actually is about, for delivering medical care, this kind of thing is about 50% of the person time is dedicated to documentation and charting things. Okay, so this is a huge component of what we do, and a lot of it is still not automated in ways that are intuitive and workable. And then clinical prediction. Okay, so forecasting how things change over the lifespan. I think I've heard a lot about artificial intelligence approaches where people really are thinking about this ahead of time. You know, this is just a snapshot taken from one of our manuscripts about how we come to make a decision based on a consensus of a committee for each individual patient who might have epilepsy. But what we'd like to have in the future would be something like digital twinning. Okay, so we have a large database of patients, and rather than relying on conversations between a bunch of experts, and it's not that that'll go away, but we want to have algorithms that have the full past knowledge of many, many different patients that have been treated with either stimulation or doing a resection or a laser ablation like I talked about, and saying, you know, amongst this past set of patients that we have that would number in the tens of thousands, which patient is this current patient we have most close to, and can we model our current patient based on those past statistics in an intuitive way? Okay, so digital twinning does have a role, I think, very soon in clinical medicine and in decision-making for patients. For those of you that may not be familiar about what it's like to be a patient and to go through the workflow that you would have in an institution, this is kind of how I think about organizing things within an institution. They'll see a physician where there's a diagnosis that's made. We talk about patients that may be relevant for surgery. There's a role for AI here, okay? We do surgical planning. If I'm putting electrodes in one spot, if I'm burning an area of the brain, or even if I'm just using a motion capture system to localize areas in the brain, machine learning can play an important role in that. We use robotics in the operating room. We have online diagnostics that are both imaging-based and electrophysiologically based in the operating room. Okay, there's a role for AI in that. Predicting how people are going to respond to the intervention that we've done. This would be another application of digital twinning. So instead of predicting who comes in and what the best therapy would be for digital twinning, it would be, in the next step, now that we've done this thing, can we predict how this individual is going to need to be cared for afterwards? You know, my research and the research of many other neurosurgeons who are scientists is working on the next generation of devices that we're going to implant. Okay, so parameter optimization, closed loop control. This is the obvious, clearest, and most compelling aspect of I think artificial intelligence for neurosurgery, at least for me. And I'm going to give you some more examples of that later. But one other thing we need to discuss is how we integrate information and multimodal data across institutions for new therapy development. In particular, Dominique Duncan, who spoke yesterday, really the types of roles that these scientists play are very important for the next generation of therapy, and they're very important for determining how the new algorithms that you guys develop, whether they're neurologically inspired or not, are going to be implemented. And so I think that there's a key role for having new algorithms that can be, taking new algorithms and allowing one to implement them from data that's aggregated across a wide variety of institutions. And I think that's something that the NIH is uniquely equipped to do, because the NIH is ultimately what incentivizes scientists and physicians and others, what incentivizes us in terms of deciding what kind of research we're going to do and how we're going to be able to do it, and giving us the funds and resources we need. So I'd like to give a couple of examples for discussion today, talking briefly about how we design devices that interact with the brain to provide a conduit to the outside world. Okay, so things like brain-computer interfacing, inducing plasticity, so trying to help people that have been injured by stroke or suffer from something like epilepsy to retrain circuits, or psychiatric disease to retrain circuits. To manage disease symptoms, this is open loop stimulation and what we do now. Thinking particularly about embodied approaches and neuromorphic approaches. So imagine you have a brain, we all do. we want to sense from the brain for these devices, right? So we have some technique that we have for recording information in the brain. I'm going to give you an electrical example because that's what we do. We have some computation and decoding that goes into this. Okay, and then we use that for some sort of internal or external effect. The internal effect would be something like brain stimulation, so retraining the brain or managing disease with electrodes implanted in the brain. But we can also interface with the outside world with things like brain-computer interfaces. And adopting an embodied or neuromorphic approach to each step might be useful, okay? And again, I'm not as much of an expert as most of the people in the room about what these two things mean, but my interpretation of them as I've learned about them have been that embodied measurements are really trying to match the measurement or the intervention that we perform to the physical scale of the system concerned, okay? And so that could be limbs in the outside world, but for me, I also think that this might include things like the scale of electrodes that we put in and matching that scale to the types of measurements that we need to make and the circuitry that we're intervening with, because the circuitry in the brain is intrinsically multi-scale, okay? It's not just within a column, it's not just within a neuron, it's synthesizing across its synapses, but it's also across regions of the brain that are spread centimeters from one another. And our hardware should match those physical scales. For neuromorphic computing, in the more general sense, I think that neuromorphic algorithms could be thought of as algorithms where the statistics of the analysis that you're doing or the processing that you're doing is trying to match the neurological statistics. And this has a very practical interpretation for, and I'm sorry, you said I could take a couple minutes, so just let me know if I'm running too long. But matching the statistics of the brain. And matching the statistics of the brain is not static. And that's an important thing to know, because the way your brain functions and the nature of the circuits in your brain, for example, when you're awake and asleep, are very different. And the way that you need to intervene with the brain when it's in those two different states is very different. I think of, this is an article for talking about translation of neurotechnologies that I think is pretty useful. We had come out recently. There's a DOI there, or a QR code there for it. But this idea of neuromorphic, or embodied hardware would be things like having microelectrodes when what the phenomena that you're looking at should concern action potentials. Or if you want to intervene with populations, you have grids of electrodes that are put on the surface of the brain. This is particularly useful for neural signals that represent aggregates of tens to hundreds of thousands of neurons, where you can look at things that obey 1/f statistics in a particularly intuitive way. You can also look at how different brain regions are interacting dynamically by putting electrodes in different areas, delivering electrical stimulation, and then measuring responses from one area to another. And if you're looking at things like the general homeostatic state of the brain, and by homeostatic, I don't mean over the course of days, but I mean the way that we control large regions of the brain from thalamic outputs to cortex, you're going to be thinking about oscillations. And these are things you can pick up even outside of the head with EEG. So the spatial scale of the electrodes that you use for these different contexts are very different from one another, but they're trying to intrinsically match the anatomy of the brain. So it's an idea of embodiment that's different from the embodiments that you would have with limbs, but the way you design your hardware should match this if you're inside the brain. Okay, this is just an example of trying to decode. This is decoding visual stimuli. The reason why I wanted to show you this is you're going to see what the patient's seeing here. There's electrodes on the underside of the brain. We're measuring two different types of electrophysiology, one that's a reflection of the feed-forward output that visual areas get from the thalamus in response to a visual input. And then the other is this 1/f type process that really reflects more local circuitry. And we can get real-time estimates of both of these features in each location that we measure from, and we can plot those into a larger dimensional feature space. But it's important in the brain to remember that this feature space itself is not static. So current systems for decoding the brain are typically reliant on daily calibration, where you have supervised routines that determine new sets of parameters for algorithmic decoding. But this is burdensome, and this is also not productive. So most of the brain-computer interfacing that you read about really only works when you have a scientist in the room with the patient recalibrating the machine day to day. Instead, our algorithms need to be able to recalibrate themselves, first of all, by trying to decode the brain in a multi-scale way, because you need to encode not just the domain specialist area, so not just the hand area of the brain, but also the general state that motor cortex is in, and its different physiology that you're going to measure that gives you the signature of those things. And we can actively probe and reparameterize the way we decode in real time and feed that into our algorithms. And I think that that should be what we think of as neuromorphic algorithms when we're thinking about decoding brain activity. And I think this would be useful for the closed-loop devices that my colleagues and I want to be implanting into the brain. Thanks.